only a 40-minute presentation, so it is really condensed. I intend to just give a brief overview of fiber reinforced concrete and talk about the benefits of fibers, and then get into testing fibers, because I think it's important, that people understand just how we test fibers to come up with the performance parameters. It's us into specifying fiber reinforced concrete. I'll share some example projects, and then I have one slide that talks about tips for successful use of fiber reinforced concrete. Okay. So by definition, fiber reinforced concrete is supposed to be concrete that's made primarily of hydraulic cements. And of course, now with the use of SCMs and everything, we would include all of the binder materials. So concrete made of binder materials, aggregates, and the key thing here, discrete reinforcing fibers. Now, these fibers are typically less than 3 inches in length, and in terms of diameter, less than 1 millimeter in diameter. Most of the fibers in the marketplace will be less than about 2.5 inches. You find them typically between, let's say, 3/4 of an inch, depending on the type of fiber, all the way up to about 2.25 inches or 2.5 inches. Now, what's important is that there are different types of fibers in the marketplace, and fibers are distinguished by the material that's used in making the fibers. So we have steel fibers, glass fibers, and if you have to use glass fibers, you need to make sure that they are alkaline, resistant. Otherwise, they will disappear in the concrete. They will actually react in the concrete. Then we have organic polymers, which we call the synthetic fibers. And then we have natural fibers, which are basically wood, cellulose, and then sisal, as well as jute. And then recently in the marketplace, basalt fibers have been introduced. Now, basalt is a rock, but then the basalt fibers are not actually all rock. I mean, they are basalt encapsulated in some type of epoxy, resin. Now, the fibers are added to the concrete at the time of batching, and they end up being uniformly distributed and homogeneously distributed throughout the concrete, matrix. Now, there is a standard specification for fiber reinforced concrete, and it is ASTM C1116. So it is the specification for fiber reinforced concrete, not for the fibers themselves. A lot of times I see that kind of error in specifications. Now, within ASTM C1116, there are 4 general classifications of fiber reinforced concrete that are delineated based on the material type that is used in making the concrete mixture. And the first type in ASTM C1116 is type 1 for steel fiber reinforced concrete. And then we have type 2 for glass fiber reinforced concrete, type 3 for synthetic fiber reinforced concrete, and then finally type 4 for natural fiber reinforced concrete. Now, as you can see, there's no type 5 or a classification for basalt fibers. And I keep on saying that until the basalt manufacturers or suppliers join ASTM, I don't think any action will be taken to include them in the C1116 specification. Now, one of the things that's important when you look at C1116 is that it's stated in there that if the post-crack performance of the fiber reinforced concrete is important, then the acceptance of the fiber reinforced concrete has to be based on ASTM C1399, C1550, or ASTM C1609. These are performance test methods that are used to test fiber reinforced concrete, the post-crack performance of fiber reinforced concrete. Now, for the purposes of this presentation, the rest of the day, this presentation, I'm only going to be focusing on the type 3 synthetic fiber reinforced concrete, because that's what's being predominantly used in most of the paving and bridge work. Now, synthetic fiber technology is primarily polypropylene, or category is polyolefin. Now, there are other types of synthetic fibers, such as which may be based on polyvinyl alcohol, but the predominant technology polyolefin. And these materials, the polypropylene polyolefin, have to meet the requirements of ASTM D7508, and I'll share that with you in a minute. One of the things about synthetic fibers is the fact that they are chemically inert in concrete, the polyolefin polypropylenes. And the best way to think about them is think of plastic. Plastic is an inert material. That's why it's such a big issue now with all the waste plastic that we have in the oceans. The polypropylene polyolefins do not absorb water, and also they don't react with alkalis, which is very, very important. And this means that when used in a concrete matrix, which is alkaline, the polypropylene fibers are very durable. Now, I talked about ASTM D7508, and I just want to share with you just briefly the requirements of ASTM D7508. Now, in ASTM D7508, there is a table, table 1, which provides conformance requirements for chopped strands for use in concrete. And there are 3 different categories that are listed in table 1. First we have micro chop strands, and then we have macro chop strands, and then the third category is the hybrids chop strands, which is a blend between the micros and the macros. One of the things that is important is what is the differentiation between a micro and a macro? And it's pretty much the equivalent diameter. So the micro chop strands have an equivalent diameter of less than 0.3 millimeters, and the macros have a diameter that will be equal to or greater than 0.3 millimeters. Another requirement, another thing also, as you can see in the table, refers to the denier of the fiber, which is essentially tied into the equivalent diameter. And then I would just like to point your attention to the tensile strength. For the micro chop strands, there's no minimum tensile strength requirement. But then for the macro, there is a minimum tensile strength requirement of 50 KSI. Now, the 50 KSI is the same minimum tensile strength requirement for steel fibers. So that's the only thing that I wanted to bring your attention to with respect to D7508. Now, there are different levels of synthetic fiber reinforcement, and I typically break them down into 4 levels, and I'm showing the first 2 levels here. Level 1, what we call the synthetic monofilament microfibers. Now, these are fibers that are used for plastic shrinkage crack reinforcement. And then the level 2 will be what we call this synthetic fibrillated microfibers. They look like a fishnet, as you can see in this photograph to this on the right-hand side in the middle. And in addition to minimizing plastic shrinkage cracking, the fibrillated fibers do provide a minimal amount of post-crack residual strength. And as a result of that, they are typically used in industry to replace the lightest gauge weather wire reinforcement out there, the 10 gauge mesh, or the 6x6 W1.4 by W1.4. And the dosage that's used for the fibrillated fibers throughout the industry is essentially 1.5 pounds per cubic yard. For the synthetic monofilaments, the dosage will range anywhere from half a pound to 1 pound, depending on the specific fiber. Now, I did say that the fibrillated and the monofilaments, the microfibers, are used primarily to protect against plastic shrinkage cracking. And as we know, plastic shrinkage cracking occurs when we have a situation where the bleed water on the surface of the concrete evaporates at a rate that is faster than the rate at which the the bleed water is being brought to the surface of the concrete. And there is this nomograph that you can find within the ACI documents 305 for hot weather concreting and 306 for cold weather concreting, as well as in ASTM C33 and the AASHTO companion document. And it essentially helps to estimate the rate of evaporation of bleed water from the surface of the concrete if the air temperature, relative humidity, concrete temperature, and the wind velocity or the wind speed are known. So this is a nomograph that's used predominantly within the industry to estimate the rate of evaporation of bleed water from the surface of concrete. Now, there is an ASTM test method, ASTM C1579, which is designed to help determine the potential for plastic shrinkage cracking of a concrete mixture. And essentially, it incorporates the nomograph. So as you can see in this slide, there is a fan. There's a heater that provides heat. There is a fan, basically, and a humidifier. So this way, the ambient temperature within the chamber, the relative humidity, and the wind speed can be controlled. And the methodology provides a combination that is used in order to be able to induce cracking in a specimen. Now, the test specimen that's used has 3 stress risers within them, one big one in the middle and 2 small ones at the ends, as you can see in here. And it essentially creates a wicking plane such that when cracking occurs due to, when plastic shrinkage cracking occurs in the specimen, it would occur right over the middle portion. Now, this is a typical slab result. And what is then done is the crack width across the section, the slab, is measured at different locations. That is averaged for the reference concrete. And then also the same thing is done for the fiber reinforced concrete. And then using this expression, the crack reduction ratio is determined. So there is ASTM C1579, which can be used to essentially look at different, the performance of different microfibers for reducing plastic shrinkage cracking. Now, this graph, the graph on the left-hand side here was a study that was done by Professor Ramakrishnan, who's now retired, when he was at the South Dakota School of Mines and Technology. And what he did was he looked at 4 different fibers that were being offered to reduce plastic shrinkage cracking in concrete. And he tested them at dosages ranging from 1/3 of a cubic yard, 1/3 of a pound per cubic yard to 1 pound per cubic yard. And as you can see, not all fibers are created equal, which means that if you just specify the poundage or the pounds of fiber that's needed per cubic yard, you may not necessarily be getting the best, performance. Now, the study on the graph on the right-hand side basically is summarizes data from different studies done by some of the gurus in fiber reinforced concrete, Neyman, Banthia, as well as Jason Wise. And in this particular graph, the crack reduction ratio is plotted as a function of the tensile strength of the fiber. And as you can see, there's really no correlation between crack reduction ratio and tensile strength. And this is one of the reasons why in 1579, there's also no tensile strength requirements for the microfibers. Next, we have the synthetic macrofibers. Now, I break this down into two different levels. Level 3 will be those that can be used, which is pretty much all of them, to replace traditional temperature and shrinkage reinforcement. So instead of using welder wire reinforcement or reinforcing steel bars, these fibers can be used for temperature and shrinkage reinforcement purposes. The level 4 fibers are some of these same fibers that can be used at a higher dosage level and for the purposes of either partial or complete replacement of primary steel reinforcement, depending on the specific application. So in situations such as concrete pipe, or sometimes in some septic tanks and so on, all of the steel, depending on the specific size and wall thicknesses, can be replaced using some of these synthetic, macro, fibers. Now, the macrofibers, synthetic macrofibers come in different architecture. They can be rope, taped, stick, or they can be a blend, a hybrid, which would be a blend of a micro and a macrofiber. The tapes are typically serrated, which means that they're scored, as you can see in here. And the stick fibers will typically be embossed or crimped so that they provide a better bond within the concrete. Now, one of the things that's important is, with the exception of the stick fibers, the tape and the rope fibers will fibrillate when added to the concrete. So this is before mixing, and that's after mixing. So before mixing and after mixing. And what this means is that when you get the fibrillation, the fiber count increases, and this can influence the paste demand. So that's something to take into consideration. Now, the fibers are added, as I indicated earlier, during the time of batching. And when they're properly mixed into the concrete, what you find is you have the fibers being uniformly and randomly distributed throughout the concrete. Some people say you get 3D reinforcement. No, it's not 3D reinforcement. This is multi-directional uniform fiber distribution within the concrete matrix. So what are the benefits of micro fibers? Basically, they provide the uniform multi-directional post-crack reinforcement within the concrete, and they bridge cracks, and this helps to reduce crack widths, which helps then with providing a tighter aggregate interlock and increased load carrying capacity. They also improve the shear strength of concrete, but this depends significantly on the type and the dosage of fiber that's used. Now, one of the main benefits of fibers is the fact that at a sufficient dosage, they will increase the ductility and the toughness of the concrete. The toughness is another name for the ability of the fiber to absorb and dissipate energy. And the big benefit of this is that it increases significantly the impact resistance of the fiber, which then increases improves the fatigue endurance of the concrete. Now, fibers also increase the moment capacity of the concrete sections. And as a result of that, depending on the dosage that's used, a thickness reduction may be permissible if that's desired. And then finally, fibers basically reduce labor and other costs that's associated with the installation of conventional steel reinforcement. So this is essentially a benefit for the contractor. And fibers overall tend to be economical relative to the use of conventional steel reinforcement for temperature and shrinkage purposes or in other applications. Now, this next slide basically three different videos that show the impact resistance of concrete. So the first section was a non-reinforced slab, and after 2 blows of the sledgehammer, essentially broke apart. The middle slab reinforced with 6x6 W 2.9 by, and as you can see here, it's been broken after 11 blows. Now, essentially, for it to be broken apart this way, it means that the reinforcement actually yielded, the wires actually yielded, and then fractured. And then in the final section, we have the slab with 5 pounds per cubic yard of a synthetic macro, fiber. And you can see that it did outlast the welded wire reinforcement. Now, this next slide is basically showing the impact resistance or the visual effect after 11 blows, which was how many blows it took to completely break the slab with the welded wire reinforcement apart. So the key thing is, how do we capture the toughness of fiber reinforced concrete? And this is where the performance test methods come into play. Now, earlier I talked about ASTM-C 1399, 1609, and 1550. 1399 and 1609 are beam tests, but basically the 1399 is not a test that the Fiber Reinforced Concrete Association, of which I'm currently president, recommends anymore. It provides an average residual stress that does not really have any bearing when it comes to design. So the preferred test method for the post-crack flexural performance is 1609 and 1550. Now, I've got a video that basically describes the 1609 test. It's performed using the regular flexural beam test. So this is a 6x6 by 20-inch beam. And as you can see here, the one of the technician is mounting the load device devices on it. Deflection measuring devices on it in the jig, and then mounting it into the load testing machine. One of the things I'd like to is the roller support system, here. And I will talk about the roller support system, later on, because it's very important. So this is what a test looks like for fiber reinforced concrete. And what you're seeing here is the bottom side, the bottom of the beam. So we have a camera looking at the bottom of the beam, and here you can see a crack forming, and also the load deflection curve. So right here at the peak load, that represents the flexural strength of the concrete. And you can see that after it cracks, the fibers get engaged and then they begin to carry load. And that's what we refer to as the post-crack flexural reinforcement. Now, as you can see in this slide, which in this case, we stopped the testing at a net deflection of about 1.5 millimeters. And it's important because in the next video that I'm going to show you, you can see the difference relative to plain concrete. But once again, the peak over here represents the flexural strength of the concrete. So by doing the 1609 test, we're able to get not only the post-crack flexural performance, but also the flexural strength of the concrete. Now, this next video is basically for the plain concrete. Now, you normally will not do 69 on plain concrete, and you'll see why in a minute. But right here, again, we're looking at the underside of the beam. Here is a low deflection plot, and look at the deflections that we're talking about. We're down 0.04, 0.05, compared to greater than 1 millimeter when the other one was stopped. And right here, you can also see what happened when it cracked. Now, essentially, because you don't have any fibers, holding the crack together, you have a wider crack, and also this will represent failure of the beam. So side-by-side comparison, with fiber, you can see the small crack width. Without fiber, you see the big crack width. So that's the difference that the fibers bring to the table. Now, typically the fiber testing, you have replicates done, and this is just represents test data for a microfiber at 5 pounds per cubic yard. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11 beams that were actually tested. You can see here, F1 is the flexural strength of the concrete. And in this case, 4.6 megapascals, which is approximately 670 PSI. And then to the last two columns, represent two parameters, the R150T, 150, and the FDE 150. The FDE 150 is the equivalent flexural strength of the concrete, and the RDT, R150T 150 is also, we also call that the RE3, that represents the equivalent flexural strength ratio, for the concrete, which is essentially your Fe3 divided by your F1. Now, remarkably, the dose response is very, very linear. And this is what you normally would find when you test fiber reinforced concrete at different dosages in terms of the response between the RE3 or the Fe3 and dosage. And this is very important, because when a fiber supplier does testing at different dosages, they're then able to obtain the dosage relationship, from which they can provide dosage for to meet a given specification. All right. Now, I talked about the roller supports before. It's important that the testing is done with the ASTM C1812 bearing support rollers. These rollers are designed to minimize friction and thereby not artificially inflate the results that you get from the 1609 or the 1399 test. So for the agency, for those who are working, look at test data, make sure that the data that you're looking at was done using the C1812 bearing support rollers. Otherwise, you may be looking at data that is artificially inflated. Now, that said, how do we specify fiber reinforced concrete? We've talked about the performance test methods. So this is just a sample specification for synthetic, microfibers. Basically, they have to meet ASTM D7508, and then also the concrete that's the fiber reinforced concrete should conform to ASTM C1116 type 3. And then more importantly, number 2, you can specify a crack reduction ratio when tested in accordance with ASTM C1579. And then for the macrosynthetic fiber, same type of thing, but then in this case, you had the minimum flexural residual strength, either FD 150 or your Fe3 when tested in accordance with 1609. Now, the Fiber Reinforced Concrete Association worked with the Colorado Department of Transportation last year, and we helped them to come up with their new fiber specification, which is a performance-based specification. But then Colorado decided to put in a minimum fiber dosage, just so that irrespective of what the minimum residual strength is, they wanted to have dosage in there as well. So this is what it is. And their requirement is that the minimum Fe3 has to be 150 PSI. And once again, the Fiber Reinforced Concrete Association worked with them to develop this specification. And I would like to offer that assistance to any entity that's would like it. Now, this is a summary of various DOT fiber specs out there. And you can see that most of the DOTs have dosage restrictions, and then they have performance requirements based on RE 1609, either RE3 or FE3, and then a few states that have 1399 specifications, and then some of them also have 1579 specifications. All right. So how do we then come up with these performance requirements? Now, ACI 544.4R has design equations in there. One for calculating the ultimate tensile strength of cracked fiber reinforced concrete based on the flexural residual strength that's measured from ASTMC 1609, and that's the expression over here. And likewise, there is also an equation, again, based on 1609 to help determine the moment capacity of a cracked fiber reinforced concrete section, based on the residual flexural strength and the section modulus of the fiber reinforced concrete. So now this is what the fiber manufacturers will typically use to come up with with design, to help designers come up with the performance parameters that are required. And then the fiber manufacturers will then use those performance parameters to come up with a dosage. All right. I would like to caution you to there are some dubious calculations out there from some fiber manufacturers, which do simple tensile. They try to equate tensile strength to flexural tension, which is very inaccurate. So be mindful of that. So in terms of projects, where can we use fiber reinforced concrete? These are some typical applications: slabs on ground, topping slabs, concrete pavements and white topping, bridge decks and bridge deck overlays, shotcrete, precast tunnel lining segments, and then various precast, concrete, elements. Dosages for synthetic macrofibers range from about 3 to 7.5 pounds. Sometimes, depending on application, all the way up to 11 pounds. And steel fibers will be typically 24 to 66 pounds per cubic yard, but then can go up to about 90 pounds per cubic yard. Applications, this was a pavement in a subdivision in Lubbock, Texas, where typically they would have been using reinforcing steel in the pavements. In Texas, they have a lot of continuously reinforced concrete in the pavements. But in this case, after doing a test project, the city engineers permitted the use of 7.5 pounds per cubic yard of a synthetic stick microfiber in lieu of the rebar, and they've been extremely happy with the performance. Other applications, I know this may not apply to Nevada, but then again, this is container terminal pavement at the Port of Los Angeles. Similar stuff has been done in Hawaii. Just to illustrate that, the fibers can be fiber reinforced concrete can be used in heavy duty type applications. This is an overlay project, a white topping project. This was done a couple of years ago in Indiana, using 3 pounds per cubic yard of a stick microfiber. And in this case, the white topping had a thickness of 4.5 inches. This is a project dates back quite a while, actually, to I think about the 2002 or thereabouts, early 2000s. But this was a welcome center in Joplin, Missouri. Again, 3-inch thick overlay over 28-year-old asphalt. And in this case, they had 3-foot joints and ended up using 3 pounds per cubic yard of a polypropylene fiber. So that's an awful lot of joints to cut. Now, some work where the joint spacing, variable joint spacing has been used in overlay type applications. So in this particular slide, as you can see, 4-inch thick test sections were made with joint spacings ranging from 6 feet to about 20 feet. And here's another project in a different county in Iowa. So to finish off, just want to bring to your attention that there are different wet products available, from the CP Tech Center. There was a study that was done that was led by CP Tech Center, looking at fibers for use in concrete overlays as well as bridge decks, and so these are available, and you can get them. And talking about bridge decks, just real quickly, Caltrans did a study back in 2002 where they looked at using shrinkage reinforcing admixtures in the bridge deck. And after 9 months, they saw a marked difference in cracking between the treated and the untreated intersection. And as a result of that, Caltrans now has the crack-free bridge deck program, which involves the use of not only the shrinkage reducing admixture, but also fibers to essentially minimize and completely eliminate cracks that will be detrimental. And Caltrans did a study where they showed that there are significant economic benefits to doing so. And again, from the CP Tech Center, there's a wet product for the use of fiber reinforced concrete in bridge decks. And the final slide that I have, just tips for successful use of fibers in concrete. There has to be an adequate paste content. This is very essential in order to improve the workability and finishability of the concrete. And more importantly, the slump has to be appropriate for the application. We've had situations where an agency stuck to their low slump requirements, and that resulted in significant balling, and eventually it cost a lot of money to fix the balling in the bridge deck. And all they had to do was increase the slump by about 1 inch or so, and that would have taken care of it. Now, subsequent to that issue, they've changed their slump requirement for fiber reinforced concrete. Batching and mixing, it's important to follow the manufacturer's recommendations in order to minimize and to prevent balling. And when it comes to pumping, thin is the height of the chute above the grate makes a difference. It shouldn't be too high. And also having rounded grates or just cutting a rubber hose and put it over the slanted grates helps significantly. Placement and consolidation, key thing is to make sure that the fiber reinforced concrete is not dragged, to reduce segregation. And then, bowl floating, don't overwork the surface. And then finally, when it comes to finishing, broom only in one direction. And also timing is very important. If you get on too early, you will bring the fibers to the surface and they may not go down. So with that, I'll like to say thank you very much. And if there are any questions, I'll take them now.
Thank you very much for your...
Sorry, I went by a few minutes.
No, yeah. That's all right. Thank you very much for a fantastic presentation. If there are any quick questions to get into the Q&A portion portion over here to the right of the screen. We can ask those of the doctor here before we get onto our next presentation. I don't see any in there right now, so I'll take that to mean you answered all the questions already and nobody has any.
Well, that was the purpose of the presentation, the way it was laid out. Thank you all for the opportunity. Always a pleasure to present to you.
Thank you very much for being here today.